Alright, more chemistry today. And the kind of chemistry that we will be doing even if you are an organic or biological chemist. Because these days, very few experiments are actually done, including by synthetic people, without detailed theoretical modeling first. So if you look at the organic chemistry division in the chemistry department, that would be people like Newton-Raphson and Richard, who do really sophisticated organic synthesis. Things like endofullerenes, fluorinated amino acids and such like, where the cost of the precursors, with this case, fullerene cages, in Lindblau's case, various complicated fluorination agents, toxic, expensive, and so on. The cost is huge. It can roll into £1,000 a gram. And the last thing you want is for the reaction you attempted to just simply not work for any obvious reasons. So no experiment is attempted in those groups without theoretical modeling first. And that involves solving some real-life equations, quantum mechanical energy equations, Schrodinger's equation. And those are rarely easy, and in many cases not even analytical. So you cannot write them down in a code form. It's not an equation, it's some horribly complicated computer problem. And so the task then becomes to optimize a certain parameter, chemical yield, energy, molecular geometry, and such like, in a way that is purely numerical, that does not rely on even so much as having an analytical expression for a function. And this is our job today. So the first item on our agenda is numerical refining. And a root, as you remember from school, is just the value at which a particular function turns to 0. So we want something like f of x equals 0, and we would like to know what is x and how many of them there are. Now, there's a great variety of root finding methods, both analytical and numerical, but I will only mention one here because it is both simple enough to permit manual processing by hand, rather than by a computer, but it is also easy enough to be derived fully, and it has a clear mathematical justification at the level that we are now at. Now, imagine we have some really complicated function, something that might not have an analytical expression, but nonetheless be continuous and have a plot. So that's how f works. And it has, in this case, 3 zeros that might be singularly hard to find, even if you know roughly where they are. The task of calculating f of x repeatedly to try and localize it might be overwhelmingly complicated because f of x might, for example, be a molecular energy in some methane containing endofullerene, 60 atoms or more. The task of calculating quantum mechanical energy for that would be a couple of hours on a large supercomputer. So the cost of a single evaluation of this function is a couple of hours on a supercomputer. How do we find that 0 or that 0? Now the solution, one of the many possible solutions, was proposed by Isaac Newton. He said, okay, let us consider not the function itself, but a tangent line. So lines that touch, for example, in here. So we know roughly where our root is. We say it's in this interval somewhere. So we drop a random point, and we call that point x0. Here, this is x0, and the corresponding value in here is and it clearly isn't going to be 0. What Newton said is, let us draw a tangent line to this graph. Like that. It is the line that eventually will cross the axis. And it will cross the axis at this point here. Now you can probably already see that the point at which the tangent line crossed 0 is closer than our original point to the root. So why don't we say that that will now be x1, so our next best guess to the location of that root. And then why don't we repeat the procedure? So this x1 here, that's its location, and that is x1. We will draw another tangent line, but at the new point. There's a red line. Our second tangent line like that. And then let us ask ourselves, where does the red tangent line cross the axis, and call that point x2. You can see it's actually so close to our intended root that it almost touches it. And then we can do the x3 and the x4 and so on. And so the point at which the tangent line crosses the axis will come closer and closer and closer. And in physics, we actually have the notion of good enough. At some point, the precision of our solution will, for all intents and purposes, practically speaking, be sufficient. Let's say 4 or 5 decimal places, and that is enough for practical decision. So we will never obtain an analytical expression, like root 2 over 3 or e to the power of log something, but it will be a number, and hence the phrase numerical finding. That number might be good enough for our purposes. So Newton actually, in his great big book, proposed this method, but the book wasn't published until 1720, I think, the book in question. And so it was Newton-Raphson that published the method first and in a much simpler form. And so this method is known as Newton-Raphson root finding method. What it rather relies on, however, is the ability to find tangent lines. So our item 1.1 is how do we find the tangent line as a function. Tangent line equations. Well, let's think about it. We have some function, and the tangent line touches that function at a particular point, so it shares the value, but it also shares the slope. So at that particular one point, the slope of the tangent line is exactly the same as the slope of the function. So, okay, we have the value. So at xn, some point xn will be f of xn. And then the slope xn will, as you know, be f prime xn, because the derivative of the function is the slope of the function at a particular point. Both might actually be straightforward to find. And then what also needs to happen is the location of the point has to be shifted from the origin, right? Remember that the slope and the intercept refer to the origin. We need to move it away from the origin to the location of our point. So we also need a shift to xn. And so the argument must be x minus xn. So if we are looking for the tangent line, what it needs to do is to fulfill all of that. So let's say y equals. Well, okay, the slope needs to be f prime. So what we are looking for is something like this, ax plus b. A is the slope, and we know what the slope is, it's f prime. So it's f prime of xn, our number. And then it's x, but x needs to be shifted. So x minus xn. And then not only does it need to be shifted, it needs to be elevated into our point, so plus f for xn. Match the value. And so you can actually easily see that if we put x equal to xn here, that this becomes 0 and we have f of xn. Then the slope of that corresponds to f prime, and everywhere else the function behaves linearly. It's a linear function with respect to x. And so that is actually the equation for the tangent point. Let's now follow good old Mr. Newton and actually write down this procedure. Well, the first thing we need to do is we need to find our initial point, and that, I'm afraid, is just experience and luck. You need to know where to go. And as chemists, you probably will, because if you're looking for an optimal pressure point in some function, you know roughly where that pressure is, right? Typically, about 1 bar or 1 kilobar if you're doing some supercritical CO2, or 1 microbar if it's a high vacuum installation. Right? You know where to begin. Then our next point will be the zero of this function, right? We want that to cross the x-axis, and therefore we want y to be 0. Okay, so then 0 equals f prime at the nth point, and then we would like the solution to this to be the next one, the next x here. And so instead of x, this is xn plus 1, the next point, minus xn plus f of xn. And let us solve this for the future point. So this xn plus 1, we need to extract out of here. Okay, I move that over to the right-hand side, and then divide this by f prime. So we have f xn divided by f prime. Xn equals xn, and there's a minus in here, plus 1 minus xn. Okay, what I'll do is I'll shift this xn over here. It'll get a plus, and then I'll swap the entire equation around. What we get is xn plus 1. The next best guess is xn minus f. xn divided by f prime. And that is called the Newton-Raphson iteration. Finding rows. Notice what it requires. It needs us to know, not perhaps to know the function, it needs us to be able to calculate the function at each point. And it needs us to be able to calculate the derivative of the function. This is not too much to ask. Typically a computer and quantum mechanical modeling program will be able to output the energy, and will be able to output how the energy changes if you move the atom around, by just actually moving the atom and repeating the calculation. So it isn't often necessary to have the explicit expression for f, so long as you have a machine or an experiment that outputs both the function and the rate of change, then you're good. And there's even equipment that does it, right? For example, the attitude control in an aircraft will output you the angular position and angular velocity, and that's all you need to know. Okay, let us look at an example of this. Fairly simple, because we have to do this by hand, but I will give you the kind of equation that it is actually not possible to analytically solve, because the equation involves a transcendental function. We have e to the x minus 1x equals 0. And we need to find the nearest root to x equals 3. Notice the difference in formulation, right? Not all roots out there, not like the general solution, just the nearest root to x equals 3 to 4 decimal places. Because presumably somebody told us that 0.01% accuracy is sufficient for the purposes of their equipment or experiment or an industrial process. Okay, what do we do? This is our f of x. F x is e to the x minus x. Newton-Raphson iteration tells us that we need the function, well, you have it, and that we need the derivative. Why don't we calculate it? Of x is e to the x minus 1. We can all easily differentiate, right? Okay, let us now construct our iteration equation. This is why I was mentioning recursively defined sequences in the very first section. This is a recursively defined sequence. So xn plus 1 is xn minus the function e to the x minus 1x and evaluated at the preceding point. So e to the xn xn over e to the xn minus 5. Well, we actually now have everything we need to know. Our x naught is 3. 3, 0, 0, 0, 0, right? 4 decimal places. When we substitute x naught here, 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 and here, this will involve a lot of button pressing on your calculator, but nothing major. Your x1 will make an appearance. x1, after you've done all the calculator work, is going to be 2.6629. Well, a lot has changed, right? We presumably moved a bit closer to the solution that we wanted, but we don't really have any sense or feeling of how close we might be. Let's take another iteration. Take this x1, put it into here, press lots of buttons on the calculator, obtain the x2. And that would be 2.5533. Well, it clearly changed again, but not by as much as the change had been in the previous step. So as you can see even here, that was the first step from the dashed line to the yellow and from the dashed red line to the red. It's the smallest step. So we are presumably getting there. Okay, next one is x3. Again, taking this and substituting it into the equation and doing the calculator work, 2.56 or 5427. Well, you can see the difference has now moved. It was previously in the first decimal place, now the difference only occurs in the second decimal place. So the accuracy presumably improves. And then x4 will be 2.5426. You can see the differences now in the last decimal place. So whatever it's been that's been making these steps at step number 4, we are clearly pretty close. And then x5 is 25426. And the difference between 4 and 5 is, I think, in the 7th decimal place. So for the accuracy that is required of us, we can say that the method has converged. And this convergence for Newton-Raphson method is quite rapid. It's what's called quadratic convergence method. You will notice that in later iterations, it very rapidly become more accurate. You can get 16 decimal places if you so wish. It's not very often in physics or chemistry that one actually needs 16 decimal places, but still. And that's the general recipe, right? You get the function or an output of some computer or a measurement device, and you just run this in a loop. Those of you who did programming would recognize a for loop. You need to know which iteration to stop, but that could be a stopping condition when the value stops changing. And this is in fact how quite a lot of numerical solvers work. And this actually, incidentally, how your calculators work. You remember, I don't know if you are actually old enough, Have you seen these ancient tables of logarithms and roots, dusty tomes in the library that your grandparents were using? It's quite obvious that something like that probably isn't contained in your calculator. Right? Your calculator, you know how a calculator multiplies, how it adds, how it divides, right? You've been taught long division and so on at school. But you might wonder how it actually does the square root, or a cosine, or you know, a logarithm and so on. This is how. So it has a Newton-Raphson iteration in there. And actually when you give it x squared equals 3, what the calculator actually solves is x squared minus 3 equals 0 using the Newton-Raphson. So it knows what the derivatives are for all the functions that are attached to its buttons, the derivatives that we programmed by the creators of the machine. And then it's this Newton-Raphson iteration that your calculator goes through under the bonnet for this equation. And of course, the solution to this equation after enough iterations is your required square root. So actually, I've just told you how most of your calculator does what I've done. Okay, so this is the root finding. Now imagine a related problem that now we are not looking for the roots, but we are looking for minima and maxima. Our agenda is numerical optimization. And I will give you two methods. One is the simple extension of the Newton-Raphson. Remember the first thing that we did when we discussed numerical optimization? In the univariate case, we concluded from some simple geometric patterns that minimum or the maximum is the point when f of x prime is 0. So instead of finding the zeros of the function itself, we are now finding the zeros of its derivatives. Well, but that's actually very easy. We already know everything here. So instead of f, we will have f prime. And instead of f prime, we will have f double prime. That's it. And it will find us the zero of the derivative. So Newton-Raphson optimization method is x plus 1 equals xn minus f prime of xn divided by f double prime of xn. And that's it. So that is the Newton-Raphson maximizer or minimizer. It will converge to the nearest stationary point. Could be inflection point, could be minimum, could be maximum. It's your responsibility to check the sign of the second derivative. But since you have the second derivative anyway, it's not too much hassle. So let us give an example of how numerical optimization is. The function in here, example, we need to find the nearest stationary point to f equals x cubed minus e equals x to x equals 1. So find the extremum, minimum or maximum, nearest to x equals 1. And find out whether it's a minimum, a maximum, or perhaps an inflection point. Okay, let's do it. Our f of x is going to be 3x squared minus e to x, and then double prime of x is 6x minus e to x. Very easy, right? And then we put the iteration group together. X n plus 1 is xn minus 3x squared minus e to the x over 6x minus e to the x. And this, since this refers to the previous point, all the x's need to be x n. And that is our Newton-Raphson iteration. Again, we are asked to do that, I think, to 4 decimal places. Our x naught is 1.0000 on the calculator. Once you've done one iteration, you get 0.9142. X2 is 0.900. So you can see it starts to converge because the difference is now in the 3rd decimal place. X3 is 0.9100. So that's it, and then all the subsequent ones will be exactly the same because the difference moves to further decimal places. So that is our extremum. We don't know whether that's a minimum or a maximum, but we can easily calculate it. So of x3, once you've done the calculator work, is greater than 0, and so as you can see, in some sense, what we are doing here is easier than what we were doing analytically. Because analytically, you'd have to solve a pretty horrifying equation that one doesn't actually have any closed form solutions, but you can express its solutions in terms of some infinite series that I will teach you how to do that in a couple of lectures from now. So, analytical methods exist for fighting these big things, but they are tedious, they are long, and increasingly, as of perhaps 20 to 30 years ago, when the emphasis shifted from just the intellectual enterprise of expanding human knowledge to the task of getting as much money as possible, as quickly as possible, that is certainly the better way to do it. And you will see this repeatedly almost anywhere you go, particularly in chemical engineering, where much of this will in fact be performed automatically as a part of, for example, instrument stabilization. So those of you who do nuclear magnetic resonance will remember these enormous superconducting magnets in the basement of the chemistry department. And there we have 2 specific kinds of problems. One is every time somebody starts constructing something, the ground shakes. And that's really bad for a supercon magnet. And so we have pneumatic bearings for them, which have a quadratic feedback control based on Newton-Raphson. And then every time some heavy truck passes around the building, magnetic field gets perturbed, and there's a magnetic field with, again, a quadratic feedback control on the fixed frequency of the deuterium nuclei. So a lot of industrial equipment actually incorporates these things already, and these calculations are done many times per second to stabilize things like optical tables, supercon magnets, and stuff like that. Okay, so this was the straight Newton-Raphson, and when this works, it's wonderful. The problem, unfortunately, is occasionally it doesn't work. And you can probably see already what the problem is in that equation that I had written. Can anybody spot the obvious problem? Yeah?
The f prime is 0.
Denominator, correct. When the second derivative is 0, which is not all that rare, it will become 0 in quite a few places in any typical function. The whole thing blows up. And this is called a singularity, and we have to find what to do. Obviously, the function doesn't behave in any way anomalously, like it might just have, a little flat region around here, where the second derivative goes to 0. There's nothing special about the function. It remains continuous, remains physical, remains acceptable, admissible. It's just that S blows up. And therefore, Newton-Raphson optimizers are not perhaps overwhelmingly common. There are cheaper and more reliable things. And I already mentioned it, it's called gradient descent. So in one-dimensional cases where, this is guaranteed to not be the case, like for square root in your calculator, everything works. So in the multivariate case, so becomes a matrix of second derivatives, and the problem that you've pointed out about having zeros in it becomes more severe. What people do instead is something called gradient descent. When I introduced partial derivatives, I already mentioned that quantity. Number f z, or more if you have more variables, is a vector df by dx, df by dy, df by dz, and further terms if you have it. As we may remember from that lecture, gradient is the direction in which a particular function grows or drops most steeply. Right? If you go along the gradient, it will grow, and if you go opposite to the gradient, it will decay. So let's draw ourselves some plausible looking function and take a look at what we can do to minimize or maximize something numerically without the need to divide it by the second derivative. So I will draw some function that has a minimum or a maximum. And here's something perhaps like that. And then we will drop that into a minimum. Here perhaps 2. And so that would be our minimum. So you can just about see a local minimum in there. Let us think about where that gradient would point. This is y, this is x, and that is y. Okay, we might roughly know where our minimum is located. So let us begin, for example. At that point, we would know the direction of the gradient. It will be a vector that points roughly along this line. In that direction, the function grows. In this direction, the function drops. So this is our number direction. Let us say we are minimizing the function. So we are looking for a minimum. Then, if that is our x0, then the best x1, given the information, would be the point that is shifted a little bit in that direction. So we can say, okay, our xn plus 1 will be xn, which is shifted down the gradient. So we subtract a little bit of the gradient division. So this will be a vector alpha number f where x is, let's say, x, y, z, and so on. Maybe we would use r as the notation here. So the next point r is the previous point r minus the gradient calculated at r. Notice this coefficient alpha, it regulates the step length. We could, in principle, take a tiny step, but then we wouldn't make any progress. We can take a much larger step, but then we run the risk of overshooting. And then we would have to backtrack. So let's say we are taking some reasonable steps. Our first step that would get us into our next one will be here. This is our next one. Okay, well, the direction of the steepest descent has clearly changed. Previously, it was in that direction. Now it's perhaps more vertical. So like that. And also, whereas the function was pretty steep around here, it is less steep around here, so the gradient became smaller. So when we take the next step, we will end up here somewhere. And then when we take the next step, we will end up here. And that's actually pretty close to where our actual minimum is located. And it stands to reason, x2, x3, that something like x5 or x6 is going to end up at the location of the actual minimum of this function. So the procedure is called gradient descent. Notice the conspicuous absence of any denominators. That is, it might actually, and in practice does, take considerably more iterations than Newton-Raphson. Newton-Raphson converges like boom, you have seen it in just a few iterations. It is not uncommon to see several hundred iterations of this method before it gets where you want it to get with acceptable accuracy. In particular, this step control is a very thorough procedure. But this is how computers do it when there is a possibility that this denominator might grow to 0. In practice, this is often used as a fallback scenario. That is, the computer begins with Newton-Raphson and then just keeps an eye on the second derivative. If the second derivative is perilously close to 0, it temporarily switches to gradient descent until the next point perhaps has a slightly healthier second derivative, and then it continues with Newton-Raphson. So the various logistical details of how this thing proceeds are perhaps unimportant, but what is important here, as you can see everywhere, is that you should be able to differentiate. This is why I've been torturing you with full and partial derivatives all this time in your classes, because they come from here. So the next item where all of this is necessary is the extension of the least squares method that I told you about in the previous lecture, called nonlinear least squares. And that's, I think, item 4. Let us again imagine a function that is either so complicated as to not be linearizable, or is not even given to us in any analytical form. Again, it is perhaps an output of some instrument. So f(t), which is only available as a value, right? So limited information. But we are nonetheless given some experimental data points. So that is time, that is the value of the function, and let us say whatever chemical model it is, perhaps has some parameters like reaction rate. So let's say it doesn't just depend on time, it's a function of some k and t, where k is the chemical reaction rate and t is time. And we are given a bunch of points, but it is quite clear that the model is not a linear function. Moreover, we know a priori that this is not a linear function from some physical considerations. We can nonetheless say that, well, nonlinear as it may be, we should still like to fit it, and therefore we must minimize the sum total of the squares of these distances. Distance from here to here, from here to here, from here to here, and so on. So the usual procedure applies, that is our derivative. It will be a function of the parameter k that regulates the shape of this function. We would like to find the best such parameter. So this would be a sum over all experimental data points, fnth experimental data point, minus our model, k computed at time tn squared, where each of these points, so say that's fm, the nth experimental point value, and that is Tn, the corresponding time at which that value has been measured, and such data sets are ubiquitous in chemistry. So then what we need to do is, of course, to minimize omega of k with respect to k. Well, we actually now know how to do it. If we were to try this analytically, we would quickly run into a problem in that f of kt is an output of some instrument. It's not possible to differentiate an expensive black box. But it is possible to find the rate of change and so on. And so we say, okay, our k next, right? So let's say j plus 1, because we've already used the n index to index into the experimental data points, will be kj minus omega prime of k divided by omega double prime of k. And that would be kj. You roughly have an estimate of what your reaction rate is from just looking at the stopwatch or something. And then that's your Newton-Raphson iteration to obtain your reaction rate that produces the best possible nonlinearity. This is how Excel does it, Origin does it, MATLAB does it, when you are asking it to fit anything other than a line. If it's a line, it uses the linear lists as explicit expressions that we have derived in the previous lecture. If it's not a line or there's limited information about it, this is what it does. If you are fitting a multivariate function or a function of many parameters, either it will do a variation of this, or it will internally switch to a variation of gradient descent. And instead of f in here, it will have omega, and instead of r, it will be a vector of the various reaction rates in there, if there are many. And if you look inside Origin, it's a little window in it that chooses the methods. You will see things like gradient descent, conjugate gradients, Levenberg-Marquardt method, and so on. You will sooner or later come across these things. The difference between them is in the choice of alpha. There are various sophisticated ways to choose the optimal step, and some of them fiddle with the direction of the descent, based not just on the gradient, but on the past history of the gradients to estimate the local curvature and so on. And so this is how your computer would actually do it. And in the remaining couple of minutes, let me just switch to the screen and show you a very typical chemical modeling program. There we go. Okay, you will come across it in some of your practicals. Let's draw some horrible molecule, like, I don't know, acetone peroxide or something like that. Okay, and then write this, and draw a bunch of oxygens between them. Oxygen, and then we need to delete the extra bonds. These hydrogens don't want, and I want the oxygens to be bonded. So this is something that a student in Bristol a couple of years ago just accidentally synthesized when they had to call the police to dispose of. Now, this is a really nasty substance that you'd rather not experiment on. Don't even think about it. But for example, we want to know the length of this bond. Right? And any X-ray machine will just detonate and get destroyed if you're trying to actually do the X-ray crystallography on this. And it's quite obvious that the way I've drawn this is pretty broken and horribly messed up. So, how do we discover the length of this bond? Well, we run quantum mechanical simulation where what is being minimized is energy, and it is being minimized with respect to the positions of all these atoms. Now we've got 22 atoms with 3 coordinates each. It's a 66-dimensional minimization. So inside it, there's a 66-dimensional hyperspace in which Schrödinger equation is being solved in real time. And you guys are lucky you're living in 2000. because this is how long it takes to minimize the energy. That's it. We now have roughly perhaps correct quantities, and we can go through some really serious quantum mechanics. So optimization methods, some silly semi-empirics that will do some approximation to Schrödinger equations, submit the calculation. It's not a supercomputer, it's just like very simple mode. Here save, submit. So it will launch a backend that does everything that I've described in the lectures. You can see the coordinates flashing on the screen in there, and lots of various symmetry things. It does it to 16 decimal places, so you can see it's being printed, and you can sort of see a word gradient being flashed on the screen every now and then, convergence, and see displacement. So we are now running a 66-dimensional minimization against quantum mechanical energies. So requested convergence, blah, blah, blah. Yeah, it might take, I think it now is at iteration. Let me see when it flashes on the screen again. Iteration 12. What is happening at the moment is this in a 66-dimensional space. Okay, so while it's running, we can actually open the intermediate result. So file, open this log for the intermediate geometries, and that's what it did after 9 iterations. And if you look at the optimization table, that's your energy as a function of iteration count. So you can see it's almost converged. And if we look at how the geometry changed, so that's the original geometry. And at the second iteration, it pulled the two oxygens a little bit further apart because we misestimated the bond length. And then a bit further, and then it got the metal groups in, and we'll probably rotate them a little bit because it doesn't like the staggered conformation. It prefers, it doesn't like the ecliptic conformation. It prefers the staggered one, so it's slightly staggered now. And you can see it actually predicted that there isn't a bond. This is a very unstable. It just flies apart. There actually is a bond. It's just about metastable, but very good. So that's something we will actually do in some of the practicals, and we will be using this program, and you now know how it works. Any questions?